BC Chemistry, Unit 4, NMR. We're talking about nuclear magnetic resonance. This kind of spectroscopy technique uses the radio waves on the electromagnetic spectrum. You can see that it's even lower in energy compared to the IR that we talked about before. So from the study design, we need to do a lot about this particular technique. But in this particular video, we'll only just cover the principles and the two kinds of spectroscopy that we need to know for NMR. One is carbon-13, the other one is proton NMR. Okay. So the theory behind NMR is that, first of all, we use radio waves. And because radio waves are really low in energy, they can't really cause any vibration or rotation of a particular molecule. What they can do is to change the nuclear spin of atoms. So the nucleus of an atom just naturally spins by itself. And a spinning nuclei works more like a magnet with polarity. So if they spin clockwise or counterclockwise, you will have different polarities. Right? So when we apply radio waves to nuclei, they will have enough energy to spin against the external magnetic field that we apply onto them. Okay? So we put them through a magnetic field and then give them radio waves. Some of them will be able to spin against the field that we applied. And when they spin back, well, its high energy state is always in an unstable state, so they will spin back. They will release the energy, and then we can detect that energy. So a spinning nuclei absorbs energy to spin against the field, and then when they release the energy, we can then harness that, detect it, and produce it on a spectrum. So only elements with odd number of nucleons will have different spins, and therefore we can detect them. So we can only use the nuclei with odd mass numbers for this particular technique. And the two that we need to know is hydrogen and carbon-13. So atoms in different chemical environments will absorb different amount of energy, which will lead to different peaks being produced on an NMR spectrum, like here. Right? Different atoms in different chemical environments will have peaks at different positions on the x-axis. Here. So what is chemical environment? Well, electrons around each nucleus that we want to focus on also have spin. And this will then shield the nucleus from the applied magnetic field. For example, in this particular molecule, let's look at this carbon. This carbon is surrounded by 3 hydrogen and a whole Ch12 group, right? So the electrons on those surrounding atoms will shield the spin of this carbon from the applied magnetic field. At the same time, this carbon is also being shielded by the number and types of atoms around it. But the shielding effect is different because this carbon is connected to different amounts of atoms and different types of atoms from this carbon. Okay? So the number and types of atoms surrounding that particular nucleus in question constitute the chemical environment of that particular nucleus. If you are in a different environment, in the case of these two carbons, you will have different kind of shielding effect on you, and therefore the amount of energy needed for the nucleus to change its spin will be different. So as a result, these two carbons will produce two different peaks on the spectrum. The position where these two peaks appear is called a chemical shift. Okay, so you notice that the nucleus, like this carbon, that is connected to a more electronegative element, like oxygen, will shift more on the spectrum. The reference. So nuclei emit different frequencies when they are analyzed in different spectrometers, which is the machine that we use for NMR analysis. Okay? So in order to produce comparable results, we need a common reference. And the lucky guy that we choose for this common reference is called tetramethylsilane. So it is a silicon atom as a central atom connected to 4 methyl groups. It's very symmetrical, very chemically inert, and can be added to a sample without causing a chemical reaction. So for us to actually read a NMR spec, we just need to treat the peak that's produced by this sample, the TMS, as the 0 on the scale. For example, on this typical NMR spec, TMS here is being marked 0. And then all the other numbers are from 0 onwards. Okay? So TMS is our scale, a 0 on the scale. Okay. There are 2 types of NMR that we need to know, carbon-13 and proton NMR, which is basically hydrogen-1. Carbon-13 NMR, carbon-13 is a naturally occurring isotope of carbon that has a nuclear spin. The most common type of carbon, which is carbon-12, don't really have a spin because it's even number nuclei. Okay? So it is used in NMR spec to identify different carbon atom environments. So we look at carbon and if they are in a different environment within a molecule. So for example, here in this molecule we have 2 carbons, and you notice because the carbon on the left is connected to 1 carbon and 3 other hydrogens, as compared to this carbon that also is connected to a chlorine and 2 other hydrogens. They are in 2 different carbon environments. The chemical shift that's produced on the spec is dependent on a carbon atom's environment within the molecule. So for this molecule, if it is going through a CNMR spec, it will have 2 peaks. And you'll notice that the carbon that's connected to the chlorine group, because it has a more electronegative element in its vicinity, so the peak of that particular carbon on the right is shifted more. Then proton NMR. Similarly, it also produces peak on the spec according to the number of hydrogen atom environments in a particular molecule. Okay? So look at this propane molecule. Due to the symmetrical nature of this particular molecule, you'll notice that all those hydrogens are sort of in the same environment. So each and every single one of them is connected to 1 carbon that's right next to a carbonyl group. If you look on this side, you'll see a similar pattern. So although we have 6 hydrogens here, we actually only have 1 hydrogen environment. As a result, the proton NMR spec for propanol will only have 1 peak.